So the first thing for Deform is exam 3 is a week from today.
You need to have the projector on.
Oh, no, I don't. Oh, I got to plug this in.
Platform.
Where's that thing? Okay, next Friday. And the topics, it's going to be everything before column buckling. So no column buckling, but everything until then. So all the beam elongation and deflection and stuff like that.
So should I memorize all of like the moment of inertia stuff? Like
No, definitely not. Everything like that will be given. Every formula will be given. And that's true in dynamics too. I didn't say that in dynamics, but I mean, you don't have to memorize any equations or formulas. Okay, so no column buckling. Anybody happen to have any questions about stuff related to the test? Okay. So now we're going back to column buckling. And remember, this is largely sort of an exercise in this important type of differential equations. And we're going to see this type of differential equations and variations of it in dynamics also. So we have this differential equation that says, well, first we're starting with pinned at the bottom. And the differential equation for a column that's pinned at the bottom is deflection double prime plus P over EI is equal to 0. And the solution to this, I'm sorry, P over EI times deflection. I missed something there. That's important. And the solution has the form V is equal to C1 times the cosine of square root of P over EI times X plus C2 times sine square root of P over EI times X. Okay? And then we used a boundary condition at X equals 0. Because it's pinned at the bottom, the deflection is 0 at X equals 0. That's the bottom. And so that says that 0 is equal to C1 plus 0. So C1 is equal to 0.
That's my kind of equation.
I know, that's a good one. And then we'll update the deflection function. C1 is 0, so this comes out to be C2 sine of square root of P over EI times X. Okay? And now we have to ask ourselves what else is going on. You know, this is for a column that's pinned at the bottom. And now we have to say, where else along the column is the deflection constrained? Well, the first type we considered was one where it's also pinned at the top. Okay? The top is at x equals L. And so that says the deflection at L is equal to 0. We don't want the trivial solutions. I mean, we know that our constraints are going to be met if the deflection is 0 everywhere, but that doesn't do us any good in this case. And so we're going to say that C1 times the sine of the square root of P over EI times L is equal to 0. And we know that that's true at, where this argument, square root of P over EI times L is equal to n pi, where n is equal to 0, 1, 2, so on. And again, this represents a trivial solution, so we'll ignore it. And we come up with, in this case, that the critical value, if you just have pins at the top and the bottom, this is what we did last time, is equal to EI times pi squared over L squared. Okay? Now, second, let's say that it is pinned at the midpoint. Okay? So let's see what the benefit is of giving this column an extra restraint at the middle. So here what we're talking about is something like that. It's not allowed to bow out at the middle. Yeah. Yeah.
Did you mean to say C2 sine?
Yes. That doesn't come into the calculation, but yeah, you're right. Yeah.
At the start, we said B double prime plus P over EI of B equals 0.
Yeah.
Is that our model just for pinned at the bottom?
Yes. Okay. Just for pinned at the bottom. And the reason is when we have fixed at the, so we'll see that the only other kind we'll do is fixed at the bottom. This comes from the moment equation, okay? And when we have it fixed at the bottom, there's also going to be an external couple provided by that fixed joint. So that's going to change the equation.
Okay, but we'll never need to use that because we already found our solution, which gives us the full.
Yeah, although a couple of the questions I think on the daily assignments are derive it, so you just have to go through the steps.
Okay, so it's just solving that.
Yeah, so it asks you to start here, and I mean, it's, I guess, start with the free body diagram and go through it, just make sense out of it to yourself. Yeah,
I know you said this is on the next exam, but for whatever exam this would we be given the original equation or the derived form?
you'd probably have to derive something because it's so simple to just plug values in, you know, like it's not really worth wasting questions on that.
Fair.
Yeah. Also, so you can think of this either one of two ways. You can think of it as just pinned at the midpoint like this, or you can think of it as pinned at the midpoint and the top. It turns out the solutions are the same. So let me draw both of those. These have the same solution. Okay, so we're going to start with what we derive for something that's pinned at the, yeah.
It can't only matter what your lowest rollers are.
Not always, but in this case it does. Because the lowest, the critical load value, and remember we're always talking about like being compressed by some P here. The lowest load value you can find, what? No.
If you have the entire column supported on its sides, then you just have the compressive strength on, right?
Hold on a second. I gotta try to get all this stuff back. Okay, what?
Like if you were to imagine like supporting that column entirely on its sides, then it would just be the compressive strength of the material, right?
Entirely what? Oh yeah, like if it wasn't allowed to bulge out anywhere, that's exactly right. You would only care then about compression, pure compression.
So in our model, is it buckling above or below the rollers?
The solution that we're going to find is going to be, so you know these are sinusoidal functions. The first solution that we found was one that bows out like a single half of a sine curve. This one is going to be the next mode that bows out above and below.
So it's gonna buckle in both
Yeah, so
segments in opposite directions.
right, so this solution is, so those are pins, and this solution is this, okay? This solution is this. Yes?
So in terms of the solutions that you're showing, would the maximum force feels like the wrong word, but the I guess the critical
Yeah.
area, would that be always between the midpoint between two either pins or endpoints or something to that effect? So like,
If you're looking for the maximum, ask again.
I think I don't really know great,
Yeah.
but if you get what I.
So if you just want this thing not to buckle and you have unlimited ability to restrain it at the different spots, then like Rais said, the maximum is restrain it everywhere along its whole length. It can't bow out anywhere. And then the only limit is the compressive strength of the material.
But the maximum would be, at the midpoint between any two, restraint points on the.
Oh, the maximum deflection.
Yeah.
Yes, you are right.
Okay.
The maximum deflection will be at the midpoint between restraints. That is correct. Because it's sinusoidal
Yeah.
functions, yeah. Okay, so, well, let's do this one. So let's start with our function that said the deflection is equal to C2 times the sine of the square root of P over EI. And we want to say V at L over 2 is equal to 0. Again, we don't want the trivial solution, so we're going to say square root of P over EI times L over 2 is equal to N pi. We don't want the trivial solution. And so square both sides, you get P over EI times L squared over 4 is equal to N squared pi squared. And so P critical is equal to 4 EI times pi squared over L squared. So that's 4 times greater than P critical if it's only pinned at the top. Okay? Yes?
I know I missed a class, but could you just define what P critical is?
Oh, yeah, so P critical is just that compressive load from the top that it's the biggest load that you can have without worrying about buckling occurring at all. Okay, so it's where it's the danger point, you know?
Mhm.
Yeah. And then you could do, you could calculate restraints anywhere you want based on this. And it would tell you the increase in the critical load. Okay, so this was pinned at the bottom. So now we're going to switch to fixed at the bottom. And we'll talk about some different configurations with a fixed joint at the bottom. This is like a pole coming out of the concrete or whatever. And so I'll start with something like this. Okay. And I'll draw a free body diagram. Of a cut from 0 to some value x. Okay. If P at the top is, if that P is being applied to the top, it means that there's no matter what the cut is, a P there and a P there. Okay. Since this is a fixed joint, you know fixed joints also apply a couple. So there's also a couple here. I'll call that M sub 0. And then there's also a bending moment here that I'll call M. Okay. And rotational Newton's second law with the about point here. And when we calculate deflection, you know, we're talking about this again. We have that M sub 0 plus M plus P times deflection is equal to 0. Because it's an elastic beam, we're going to assume that M is equal to EI V double prime. So this equation becomes M sub 0 plus EI V double prime plus PV is equal to 0. And if you rearrange these, you get V double prime plus P over EI times V is equal to negative M sub 0 over EI. Okay, so that's the governing differential equation for fixed at the bottom. And now here is an important little fundamental fact about ordinary differential equations, okay? We're going to call this the particular equation. And we're going to call that without the particular equation, notice in this case, has some stuff going on that isn't multiplied by V or any of its derivatives, okay? So this has no, this has a term with no deflection or derivatives, okay? And now we're going to look at this equation, removing the thing that has no V, V prime, or V double prime, and that's going to be called the homogeneous equation. So V double prime plus P over EI times V is equal to 0 is called the homogeneous equation. So this is where you get rid of the terms with no V, V prime, or V double prime, okay? And the general solution to the particular equation is, I'll call it VH plus VP. okay? This VH is the general solution to the homogeneous equation. And this VP is any single equation you can come up, any single solution you can come up with to the particular equation, okay? So any single thing you can come up with that solves the particular equation. Okay, anybody have any questions about that? That's a very common strategy for solving differential equations where you have one of these terms that's not multiplied by v prime or v double prime. Yeah.
So these equations are used in conjunction with each other. It's not like you use one over the other.
That's right. I only defined, I mean, like, because the question, like, why do we care about this? This doesn't represent anything, you know? But we care about it because this happens to be true. So we're going to come up with a general solution to this, which gives us every possible solution to this. And then we're just going to try to find one thing that solves the actual equation we care about.
This is Calc 4.
Yeah, I assume so. I've never taken Calc 4, but here.
Should last.
Yeah. Okay, so what's the solution to the homogeneous equation? Well, we've already seen that one. You know, VH is C1 times the cosine of square root of P over EI times X plus C2 times the sine of square root of P over EI times X. Okay. Now we just need to find one thing that solves the particular equation. Okay. So now we want any single solution to the particular equation. Okay, so what can we use? Well, notice if VP is a constant, then VP double prime is 0, okay? So the particular equation just becomes we can write it as like VP double prime plus P over EI VP is equal to negative M sub 0 over EI. And this is 0 because we're assuming it's a constant. And now we can just solve for that constant. VP, those cancel, is just equal to negative M sub 0 over P. Okay? So the solution to our particular equation, the full general solution, is V equal to C1 cosine of square root of P over EI times X plus C2 times the sine of square root of P over EI times X minus M sub 0 over P. Okay? And now we're going to go to the boundary conditions. We'll, just like we did with the pinned case, we'll start with the boundary conditions at x equals 0.
I have a quick question.
Yeah.
So why did we assume that BP was constant?
Because we're just trying, basically, if you're trying to find the general solution, there's a lot of thinking involved in that. But if you're just trying to find one single particular solution, you're just looking for anything, any single thing that'll work. And so if you look at this, I mean, I can't say that I thought of this on my own, but you can imagine someone smarter than me thinking of this on their own, just like, okay, well, we have the deflection in here, right? Let's try functions for the deflection where this is going to be 0. Then that makes this equation a lot simpler to find a solution for it, you know? Two different kinds of things would work. I mean, like, what's a function that always has its second derivative equal to 0? Any linear affine function, you know, satisfies that. So we could have assumed the form v is equal to like ax plus b. Since then this would be 0 when we took the second derivative. Then we'd set that equal to this. We'd see that the linear term goes away and we'd come up with the same solution.
Okay, so assuming BP is a constant is, for lack of a better phrasing, just the simplest way.
Yeah. I mean, really, I think the easiest way to think of that is like, you're just trying a bunch of stuff, seeing if you can get something to work.
Gotcha.
But it's the fact that this term is here is what made it easy to do, you know?
Mm-hmm.
Okay, so now we're doing the boundary conditions and we're going to start with these two boundary conditions that say the deflection is 0 and since this is a fixed joint with the ground, V prime at 0 is also 0. Okay. Well, let's start with V prime of 0 is 0. V prime, if we take this derivative, is that first term is a cosine, the derivative is going to be a sine, so we have negative C1 times square root of P over EI times sine of the quantity square root of P over EI times X plus C2 times the square root of P over EI times the cosine of square root of P over EI X. Okay? And now we're going to say that, you know, we're going to set X equal to 0 and say that that's equal to 0. This function is equal to 0 there. And so if you plug in X equals 0, the sign goes away. But C2 times the square root of P over EI, cosine of 0 is 1. So we have that this is equal to 0. And that tells us that C2 has to be equal to 0. And so now we're going to update our function. And so V is equal to C1 times the cosine of square root of P over EI times X minus M sub 0 over P. Any questions about that first step? Yep.
So, is there any way to like avoid getting the trivial solutions on the first step? Is that something that you'd ever consider doing? You know, 'cause
No, because you have a lot of stuff still in your, first you need to get a bunch of stuff out of your equation so you can get to the simple argument for the sinusoidal terms. So we first start by eliminating anything we can, and then we can look at the argument inside the sinusoidal. Yep.
We might be heading in this direction,
Mhm.
but, so if it were to be fixed at the bottom and like pinned at the midpoint or at the top or whatever, would it be similar to the previous equations, just with the minus MO over EIC as the other?
Yeah, it is going to be. It's going to be the same approach, and we're going to get a similar form. It's just we're going to eliminate the stuff that we can and find constants that we can. So now we're going to go. So now that we've done the easiest one, happened to be V prime is equal to 0 at x equals 0. Now we'll say V at x equals 0 is equal to 0. Okay. And we're going to use this updated form. So we have 0 is equal to, cosine of 0 is 1, so this is C1 minus M sub 0 over P. And that tells us that C1 has to be equal to M sub 0 over P. And so our updated form says deflection is equal to M sub 0 over P times the cosine minus M sub 0 over P. So this is for fixed at x equals 0. And now we'll consider what's happening at the other ends. Question?
Would it be easier just to factor it out, or would that make?
Yeah, actually, I've seen people factor it out.
Okay.
I like the looks of it this way better, but yeah, that does get it sort of a fundamental thing here. We got because now you sort of go like, oh, okay, like that cosine can be equal to 1 at certain spots, you know, and that's what we're going to end up looking for. Okay, so now we're going to use, and what you need to notice is that this is exactly the same set of steps that we used in the pinned case at the base. So now we're going to use the boundary conditions at x equals L. Okay. The first case we're going to consider is free at the top. Okay. So that's one where it starts out like this. You apply the load, and it does this. Okay. What is the So if all you have is a force acting at the top, and this is the free end, so we're not applying a couple to the top, what you know here is that the bending moment at x equal L is equal to 0, okay? And if the bending moment is equal to 0, so M at L is equal to 0, and that means that V double prime at L is equal to 0. Because of the elastic beams relationship, you know, this is from the fact that M is equal to EI V double prime. So that's going to be our boundary condition. Okay. And so I'm going to take the second derivative of this, V prime of x is M sub 0, this was a cosine, so it's negative M sub 0 over P times square root of P over EI times sine of square root of P over EI times x. The derivative of the constant is 0. And now I'll take a second derivative, and I get negative M. I'm multiplying by another P over EI, so the P's cancel, and we get negative M sub 0 over EI times the cosine and so the boundary condition says plug in L for x, and you get square root of P over EI times L is equal to, for the cosine to be equal to 0, we need n pi over 2, right? And that n, we need this to be, okay, so this is equal to n pi over 2. And what are the n values we can have? We can have 1, 3, 5. And so now square both sides, you get P over EI times L squared is equal to n squared pi squared over 4 for n equal to 1, 3, 5. The lowest force is going to be at n equals 1. And so our P critical is equal to EI times pi squared over 4 L squared. Okay, so in the case where we had pinned at the top and pinned at the bottom, like notice these all have the same form. It's all EI pi squared over L squared, and then just multiplied by some coefficient, okay? When it was pinned at the top and the bottom, the coefficient was 1. When it was pinned at the middle, the coefficient was 4. That critical load was 4 times as big. Now it's fixed at the bottom, but it's free at the top. The coefficient is 1/4. This can only handle 1/4 of that compressive load from the top as a pinned at the bottom, pinned at the top case. Okay, we'll go through and compare all these at the end. I'll make a table. But what I really want you to follow is sort of the process of thinking through this, partly for this class and partly because this type of differential equation comes up over and over again. Yep.
So, if you knew, thinking like industry-wise, if you knew what your critical, heat critical was, you could work backwards to see
That's true. Yep.
where, how many pins you might need, where you might.
That's right. Or how thick it needs to be, how long it can be. Yep. All the relationships between those things. Any other questions?
If you reinforce it all the way along, do you have to worry about your reinforcement?
I suppose that's probably true. Yeah, reinforce it with 2 other columns.
Kyle, let's say you had like a long beam that was like supported at multiple like even intervals.
Yeah.
Could you break it down and do like the first interval, let's say, and then extend like your sinusoidal wave?
Yes. Yep, that's right. Notice this solution to this one where we have it pinned at the middle. That doesn't have to be pinned at the middle, really. It really could just be pinned at the top and be half as long, and it's the same solution.
But if you have multiple of those, you have to treat your longest section for P critical.
If you what?
If you have like pin here and here, you have to evaluate.
If it's not equal intervals, then you have to do the whole thing at all of those. You have to use boundary conditions at all of those points because the nature of this beam wants to be a sinusoidal function. So if this beam doesn't want to have a quick thing here and then a long thing here, that's just the nature of the elastic beam.
So,
And you can see that from the form of the differential equation.
so if you had something like that, you would have different P critical values for different lengths. Like if you had a length of like maybe 2 meters up here and then 1 meter.
You'd have to do it all as a single beam and do all those separate boundary conditions. You can't break it up like that. The only time you could break it up like that is, like Ray said, if it happens to be at uniform intervals, then the equation's reduced to that. But really what you should do is just always use the full beam and use the boundary conditions, Because for one thing, you won't make mistakes. And for another thing, it reinforces your memory of how to go through these problems,
Fun.
It is fun. Maybe not as fun as figuring out the error in acceleration measured on the surface of the Earth, but this is the second funnest thing we've done this morning. That's for sure.
This is a lot of calc right here, so.
Yeah, it's a lot of, that's for sure. And the cool thing is for all you guys, not Joy's not here, is that starting on Wednesday, we're going to see like almost this exact same stuff again in calculating simple harmonic motion.
Is that a good thing, or do we?
It's good for you because you get half of your studying is for free, you know what I mean?
That's fair.
Well,
There's the silver lining.
Yeah. Okay. Have a good weekend.